a bit about Alan. Thank you, first of all, Alan, for joining as chief guest. We are really privileged to have you supporting our ACM plus IEEE Computer Society organized this event, and we are really lucky to have you on with us. And here is Alan's great profile. I'm really thrilled to share these. So, Alan, I think we all need to take inspiration from this executive profile which we have. So, Alan has been a past section chair, and he is relentlessly working towards many volunteering activities in STEM, which he's going to talk in a few minutes. But yeah, I will hand it over to Rashid, who is our vice chair, to give the address.
Hey, good morning, everyone. Thanks for joining. I see the crowd is a little light today, but yeah, usually, yeah, we get a lot of crowd. But yeah, yeah, thank you so much, Alan, for accepting the invite to be a guest speaker. We are very happy to have you and learn from your experience and your learnings. That's going to help us with the technical community. And me as a vice chair, main role here is to expand the technical community in the Richmond area. So that's why we have been partnering with the IEEE Computer Society from the ACM side and trying to have these more frequent sessions to bring all the technologists together in the Richmond Society. Yeah, and once again, thank you so much, Alan. And I'll hand over it to Kader for a quick intro.
Yeah, thank you, Rashid. Thanks. Yeah, first of all, thank you so much, Alan, for accepting our meeting invite and joining here as a chief guest. And Alan is, he's such an inspiring person. We met in person in the last of our IEEE family picnic event, and in that, the stories, the presentation, the what we call the real robotics presentation, what you presented on that day, it was such an inspiring uh, and that's very great to have Alan today with us in this series. And thank you so much. I'm looking forward to collaborate more on the STEM projects, whatever it's collaborating in the IEEE series, Alan. And yes, yeah, so I'll give the next to the Deepanjan, our ACM.
Yeah, thank you, Kader. Good morning and welcome everyone. I'm Dipanjan. I served as the secretary for the ACM Richmond chapter, and it is great to see that both the ACM and IEEE community is coming together like this. I'd like to echo the welcome note to our chief guest Alan Jones and speaker Shailesh Kadam. Thank you both for being here to inspire the community. And we are thrilled to learn from your experience and insights for the today's session. I'm not sure if Ankita is here.
Yeah, we can skip a bit and
Okay.
give it to Alan.
Then I go to Alan, yeah.
Yeah, I can stop sharing, Alan.
Okay. And I will go ahead and let me shift my screens around here so that I get to the right one for you to see. Between PowerPoint and Zoom, everybody wants to move your screens around. So rather than put PowerPoint in the real presentation mode, I'm just going to share it the normal way here. So let's see. Can you see the screen that says Mission Tomorrow on it?
Yes.
Okay. Okay. So, like I said, normally I'd put this in presentation mode and I'd have the nice monitor off to the side with all the notes and all that kind of stuff. But rather than battle with that, I'm just going to go through it like this. When I go through the slides, some of them aren't going to have a lot of text, but when you get the slides later, if you look at them, sometimes you'll see notes down here. So if I say something but it's not on the slide, and you want to, track down the information, just look in the notes. Okay, so what I'm going to talk about is something called Mission Tomorrow, and it happens every October. This year it's going to be October 20th through the 22nd, and it's held in International Speedway. So first, a little bit about IEEE and its educational focus. If you look at IEEE, education is a core part of the focus of IEEE. In fact, if you look at the legal documents that set up IEEE, it's defined as an educational institution. So its focus is on education for professionals and also education for college students and educational for K through 12. So it's a very core, integral part of it. And some of the things that it does even stretch beyond what you would traditionally think of as something IEEE would do. So, for example, there is a website called tryengineering.org, and it covers all kinds of fields of engineering, not just electrical, not just computer, civil, chemical, you name it, it's in there. IEEE is the one that's responsible for the overall maintenance and operation of that website. Even though it doesn't create all the content, it covers all the operation stuff to keep it going. So tryengineering, excuse me, tryengineering.org provides totally free resources to teachers, students, and parents for K through 12 students. And it's organized by age level, content, all kinds of different ways that you can slice it, dice it. You can get lesson plans, you can get activities, you can get free resources. There's just a huge amount of stuff out there on that site. So they maintain that. They also have another website called reach.ieee.org. And whereas tryengineering.org looks at STEM from a STEM perspective, from a science, technology, engineering, and math perspective, reach.ieee.org is really made for like social studies teachers, looking at the impact of science, technology, engineering, and math on the history of the world, on the influence on cultures, on society, all the ethical considerations and all that kind of stuff. So it also has all kinds of free resources, free lesson plans that teachers can make use of, that kind of stuff. So there's a lot of education stuff that IEEE does. And also you might think of IEEE, okay, Institute of Electrical and Electronics Engineers. They do electrical stuff. That's what IEEE does. It's just electrical and electronics. When it was originally founded, well over 100 years ago, that was true. But for example, its involvement in computers stretches all the way back to when there was literally one computer in the world. Its first conference on computing topics was when there was literally one computer in the entire world. So, its website is computer.org. You think about what did it take to get the website computer.org? You had to be involved awfully early to claim the title computer.org. So, there's lots and lots of stuff that IEEE is involved in because computers and electronics are involved in so many things in our world today. There's like 39 different technical societies that make up IEEE. So, locally, we've got the Computer Society chapter, we've got the Power and Energy Society chapter, but we also have biomedical engineering. We also have magnetics, not magnetics as in a compass. I'm talking about magnetics as in spintronics used to switch communication circuits in femtoseconds kind of time frames. There's the self-driving cars, there's the oceanography society, there's just lots and lots of stuff. But as far as coming back to the education part, locally, STEM outreach, K through 12 STEM outreach is one of our biggest budget categories. We spend as much, I'd say it's probably one of the top 2 or 3 budget categories in terms of, what we prioritize we're going to work on. So when we started doing STEM outreach, we kept running into these challenges. You would put all this effort into it, and you didn't seem to make real progress. So the things that we encountered, and we'll get to the solution in a moment, but the things that we encountered is if you want to do STEM outreach in schools, you need good contacts in those schools. The schools won't just let you come into their school and talk to their students. They're very leery of people they don't know, people they don't trust, and understandably so, because there's lots of strange people out in the world, and they can't take a risk at having their students hurt. So until they know you, until they trust you, they don't let you in. So you've got that kind of a thing. So you might have to work with the teachers and the administrators for a while, before they trust you. But then you run into the next problem, which is there's a very high turnover among teachers and administrators within schools. There's a lot of burnout, and that's not just in schools that struggle, it's in schools that are top tier schools. It's a very stressful career. A lot of brand new teachers last 1 year and then they go, wow, this wasn't what I thought it was going to be. So you might make a contact, but then find next year they've either switched to a different school or they've, retired, or they've just left teaching altogether and gone off to some other career. So then when that happens, you're back to square one. You're trying to make a contact, and then you go through the cycle again and again and again. And it's like, how do we get past this point? So we learned about something just last year that really, really helps with that. And it's called Mission Tomorrow. So Mission Tomorrow is a joint effort of the Richmond Chamber of Commerce, and they go by Chamber RVA, and Junior Achievement. So Chamber RVA provides the industry resources. They're the, the company that, or they're the organization that companies in the greater Richmond area join to be the central voice of business, I guess you might say, in the greater Richmond area. And they partner up with Junior Achievement, and Junior Achievement's focus is helping students connect the school world to the work world. Teaching them things like financial literacy, so that they can understand why it is they need to know math. You're not going to be able to manage your finances, which you're going to need to do if you want to live, if you don't understand some basic math. Things like that. So they have an entire professional staff whose sole job is to maintain the contacts with the schools. They understand the situation of this teacher leaves, that teacher comes in, all that kind of stuff. They've got people, that is their sole job, is to maintain those contacts in spite of all the turnover, in spite of all the everything going on. They keep those contacts in place. They've got the superintendent of every school system in the area on speed dial. And the superintendent of every school system in the area has them on speed dial. They know each other. It doesn't matter that the principal at this school left. The superintendent of schools knows who you are, and the superintendent of schools will make sure that the new principal connects with them. So they take care of all that stuff of, that's frustrating for us, of trying to hang on to those connections. They take that burden off, and they and Chamber RVA work together to pull off what they call Mission Tomorrow. And Mission Tomorrow is a multi-day event. I forget how many years they've been doing it in a row, but it may be like 10 years in a row now or something like that. And I can't believe that it took us as long as it did to learn about them. I guess maybe part of that's because I haven't got any kids, so none of them were in the 8th grade, so I never heard about them. But Mission Tomorrow is a multi-day event. It involves almost every single 8th grader in a public school in the greater Richmond area. So last year, over 12,000 students came through the Mission Tomorrow event in the course of 3 days. That's a lot of kids. So, they take care of all of that stuff so that we can focus on the STEM outreach itself, or they don't just cover STEM, they cover all careers, but we can take care of that. We can take care of that outreach. So, the idea of Mission Tomorrow is the area companies and organizations are showing 8th graders different career options. So it's not that you're trying to get the students to where they're experts in your career. You're just trying to expose them to that as an option, because at this point, they're figuring out what electives to take in high school and stuff like that. And if they haven't taken any of the STEM type electives, then it's going to be awfully hard for them to major in a STEM field when they get to college. If they only took the bare minimum math classes, if they only took the bare minimum science classes, than to expect them to suddenly become software engineer. That's an awful lot to ask. So the idea is to expose them to it, get them curious about things while there's still time for them to, investigate what is this thing that they told me about. That sounded kind of interesting. Maybe I ought to talk to the guidance counselor about that and, find out what I ought to learn some more. So they have waves and waves of students coming throughout the day. It's staggered so that different streams of school buses are arriving throughout the day, and this school bus arrives and all of the students in that school, or maybe several school buses, go to building number 1, and they're going to spend a certain amount of time in building number 1. And then as soon as they're done with their time in building number 1, they're going to move to building number 2, and another wave of school buses is going to come in, and they're going to go to building 1, and it's going to keep on rotating on throughout the day. So the waves of students come in like 15-minute intervals. To give you an idea of how precisely they have it timed, it wasn't technically 15-minute intervals. It was 14-minute intervals. They had it timed to the minute. It was, okay, 2 minutes until all the students have got to be out of this building. It's time to finish up and go to the staging area to move to the next building or to the next room. So it was organized chaos is the best way that I can describe it. They had it, the Chamber RVA junior achievement part of it was organized, but anytime you have that many 8th graders, it's chaos. So they managed the chaos and kept things flowing. It was just our job to, interact with the students, get their interest, keep them engaged, that kind of thing. So even though it was chaotic, it was some of the most fun chaos you can imagine. You've got lots and lots of students. Some are, more interested than others, but there are lots of interested students here. So, the key things were that Chamber RVA and Junior Achievement handled all the logistics. They handled all the get the food to the right people at the right time, get the students in the right place, get the, make sure all the chaperones are there, make sure all the security is there, make sure all of the, everything is in place. The companies just handle their own booths and their own volunteers. That's what the companies get to focus on, so that we don't have to focus on the stuff that's not fun. They try to make it very easy for the companies and the organizations to do the part that is interesting to them while they take care of all of the make it happen kind of stuff. Okay, so what does it take to have a successful booth if either ACM decides to participate, or one of your own individual companies decide to participate? What does it take to have a booth that's a success and not a booth that the students skip over because they've got very short amounts of time to go to the booths in a given room? There might be a dozen different companies in a particular room, and they've got 14 minutes to see all the stuff they want to see in that room. So why should they go to your booth and not somebody else's? So, well, first of all, you've got to catch the students' attention very, very fast. It's not something where you're going to have them come by and spend 5 minutes deciding if they want to look at your stuff or not. You know, if it takes you that long to get their attention, it's not going to work. So, and that's because they've got so many different options that they can pick, you know, and all those options are trying to get their attention. So you've got that very short time to make your pitch. And you've also got to remember that they're eighth graders on a field trip and they act like it. They're all keyed up. They're all excited. They're all out with their friends. You know, how do you catch their attention when they've got all that, you know, activity going on? So part of it is you have to make your booth hands-on and fun. If you want to give them a poster session on some technical topic, you are going to lose them. They are not going to want to listen to it. They're going to walk away. You've got to let them put their hands on something, and you've got to make it fun. And again, what you're trying to do, you're not trying to make them an expert. You're trying to get them curious. You need to try to get it to where when they go back to school and the teachers say, okay, now what kinds of things got your interest up? You know, they'll remember something that you showed them. They'll want to talk to the guidance counselor or to their teacher about, if I want to go into something like that, what do I need to do? You know, what kind of classes do I want to take? So at this key point with this particular set of students, that's what you're trying to accomplish. You know, different ages, you're trying to accomplish different things, but that was one of the key things that the people at Junior Achievement, you know, told everybody, don't forget, you got to make it fun. You got to get their attention. You got to maintain their attention. So, you know, some of the things that we did in last year's exhibits, we were trying to show them some of the breadth of things that IEEE members get involved in while still connecting it to things that would interest them in some way. So, you know, one of the things that that IEEE members are involved in is basic electronics and radio communications. So rather than just have some, you know, circuit that didn't mean anything, we had them tune to their favorite radio station. This is the station they wanted to listen to. And here's what the signals look like that are coming from your radio station. And here's how the audio shows up over here. You know, it shows up like this on this kind of a station and like that on that kind of a station. And you know those little words that show up on your radio saying the name of the song? See this little part of the signal? That's where that comes from. You know, so that at least it was something they connected to and not just yes, the emitter of the transistor is hooked to the resistor over here. You know, they don't want to hear that. If you can get them interested, yeah, later on they'll learn that kind of thing. We had demonstrations on robotics, and it was with robots that were made to teach robotics, both the programming and the circuitry and all that kind of stuff specifically designed for students their age. And just show them some of the stuff that the robot can do. And they go, well, could you make it do this? And we could tell them, well, if we had a little bit more time, we could show you how to do it. But you can learn how to do it yourself.
Ellen, I'm sorry to interrupt. By considering the time, we need to we have the Shailesh presentation as well. Can please go a little bit quick, Ellen? I'm sorry.
Okay, I'll finish up real quick. So, we also had artificial intelligence, emotion recognition, and they were posting themselves on social media, making faces at the camera, or AI-based pose estimation. And that was one that caught their attention even at a long distance. They saw stick figures superimposed on themselves and came over and said, "What's that?" So you've got to get their attention and do it quick. One of the things that we found that was an unanticipated benefit for us is it drew a wide range of volunteers from our organization. More than any other activity we did, it drew volunteers from all backgrounds, all ages, all the way from senior, retired engineers to college students who were still in school who wanted to tell, rising high school students about what they were doing in college. So most of the new volunteer officers that we've got in the subunits of IEEE started out as STEM volunteers. That's the thing that caught their attention and made them get involved. So that was a real benefit for us. So then just the final slide. I wanted to mention that ACM and IEEE cooperate on lots of different stuff. You can actually join the Computer Society without joining IEEE, and there's a link there that talks about how to do that. And also there's a free computer magazine that's kind of a summary of some previous articles that appeared in all of Computer Society's numerous different magazines and journals and stuff like that. And that's the link you can go to. And again, as I said, it's free. So thank you for your time.
Thank you so much, Alan. This is a great one. So we will move to Shailesh and then come back for final closing remarks with you, Alan. So
Yeah.
to Shailesh.
Thank you, Alan. It was really insightful. When I was in my school, I never know what I had to do. I never had access to computers, but what you're doing is absolutely amazing for all the people, for all the students. I wish I would have got somebody like what you're doing. Maybe I would have been in a different field altogether. Let me share my screen. Are you able to see my screen now?
Yeah, we can see.
Yeah, yes, we can see.
So my presentation is on the invisible weight of the web. So if you look at web pages today, they actually carry a lot of videos and images and a lot of JavaScripting running behind the scenes. So how do we make it a little faster? So I work in Size Global, which is the retail brand currently in New York. So one of the things that we do is we sell products online. We acquired Neiman Marcus last year. So we are one of the topmost brand right now. So essentially what we're trying to achieve here is customer experience on the web as well as on their mobile phones. So I'm going to talk something about how this web page compression algorithms are currently working in the industry. So every second counts in our business. So currently, if you look at the web pages today, an average web page would have around 2.3 MB of size, including all the images, videos, and everything. And based on the study, it is observed that more than half the people will leave the website if it is the load time is more than 3 seconds. So and then we have to be extremely optimized to see that the web pages are very fast and they render within a second or so. And there's a lot of revenue loss if customers are not hooked on the website, and it's estimated to be around $2.6 billion. So there's a cost saving that which we're trying to achieve using this compression algorithms. So what are the things that take the web pages down? One of the things that most of the thing is the images. So those are the things that if they are not optimized and if they are not smaller in size, that's where the web page actually starts rendering a little later. Then there is JavaScripting for animation. There are fonts. There are cascading style sheets for how the web page looks and everything. Then there's a less amount of videos and images that come in. So that's where we are trying to optimize based on how the web pages are built in today's scenario. So now let's look at the compression algorithms, right? So we are looking at text and data first, which is basically HTML pages, cascading style sheets, fonts, and other texts. Then we look at images for compression next, which Google has worked on several of these, which is AVIF, WebPage2, and JPEG XL. And then the third thing is the assets. Assets are basically animations and other images which are in sequence, but they are stored in a code repository and then they are accessed during runtime. So we're looking at compressing in these three areas as of now. So in 2010, Google came up with a new compression for the web, which is used extensively across all the web pages. So if used broadly as a compression algorithm, it's definitely going to be compatible across all the different websites and web pages. And what it does is, if you look at this dark green color, it's able to compress HTML, JavaScript, and CSS much more than what it used to be before, which was gzip. Elon Musk built gzip, which was actually sold to a company, and that was used previously. But using Broadly's Google compression, it basically gives us more compression without losing much of the data. And 96% of web browsers use Broadly as a compression algorithm, so it's compatible. So how does Broadly work? I'll just give a short introduction. So if you look at texts, if they're repeating texts, so it knows where the length is and where the destination is. So this length is 5 and the destination is 8 for this. And the length is 5 and destination is 5 for this. So what happens is the first time when it sees a sequence, it's stored as it is. But next time it sees the same sequence, it doesn't store the string. It stores the length as well as the place where it has to be inserted in the file. So it will store A, B, C, D, E as it is. But next time it stores just the numbers where this string is going to get replaced with and what's the length of it. And this way it goes on compressing the entire HTML page. So how does that work is Broadly has a series of data dictionaries. So when you use a web page, we have image tags, we have div tags, and we have hyperlink tags. So all of that is stored in a static data dictionary. So every web page has a static characters inside it, and Broadly knows what those are, and that's the reason it is able to look up at that table and then find what that value is, and it stores that in a file. So essentially, we're not storing the entire tags, but we are storing a number to that lookup table. So all of this is heavily compressed just with the offset from where the value is from. Broadly actually is able to look at a larger file around 16 MB. gzip was used to look only 32 kilobytes, so it looks at a larger window to compress. And it only stores distance and length, so it's much faster compressed. So there's something called as Huffman coding. Huffman coding is basically a huge table, and it has all the values assigned to all the alphabetical characters in a sentence in English alphabets. So after looking at different strings and texts, we know that the letter E is extensively used in majority of English words. So what we do is we store it closer to the root and we assign a bit to it, which is 0. So instead of storing E, we store a bit value, which is 0, and it's closer to the root because we know that the traversing this E in a compressed tree is going to be much faster than traveling O or traveling T or E. So if you look at every letter is assigned a bit, and that way we are able to compress it a little faster and traverse it really faster based on how often it is seen in a text or on a website, on a web page when the description is written. So that's how it is determined. So we have to travel a tree to find what these values are. Now, if you look at these tags here in HTML pages, we have this less than tags. So it knows that, okay, this is a tag to be used, variables, colons, HTTPs, all of these are stored in a Huffman table, and they are stored separately so that we only know the offset of it and not the entire string. So the sequence looks like you are pre-processing, you're reading the entire HTML page, then you do LZ, that is called as LZ77 mapping is the one which I showed you, which stores the distance and the length. Then there's a dictionary lookup for those static words. Then we do context modeling, that is we just understand for that particular set of 16 MB length of data, what is that numbers that we need to store. And then there's entropy coding, basically storing 0 or 1 instead of the string. The next algorithm that we have, what we saw is broadly, but Facebook came with something superior, which is Z standard. It's used for parsing API based strings. When we watch Facebook or WhatsApp, an API call is made to the end service, and it actually sends a string or data at real time. So what it does is basically Z standard, what it does is instead of, it uses LZ77, which we did before, but instead of using Huffman, it uses a 4 kilobyte payload message. It actually shrinks the entire page or whatever the message is into a length of 4 kilobytes. And instead of going to a tree, it stores it in a cache. So it's much faster. We don't traverse a tree. We actually look up a table to understand if the pattern has arrived before. So the compression is much faster. It compresses around 1400 MBs in a very high stream of data. So it's the same thing. Essentially, block splitting. It splits into 4 kilobytes of each. It does that pattern matching, and it does as and this entropy is a little different in Facebook's Z standard because it doesn't store zeros and ones. It stores in fractions. So it's not just zeros or ones. The bits are a little smaller than what Broadly does. So that's the reason why the speed is a little less, because it has to traverse the not the tree but lookup table. So it takes a little bit of time, around 800 millibytes per second, to parse the entire message. And it's a flat straight array, not a tree. So if you look at this, what now you might be thinking, what if the strings are appearing less in a smaller file, right? Because if the file is big, then the probability of string appearing multiple times is higher than the one with a smaller file. So how do we solve that? So we solve that by using training data. We train the model basically looking at our data. So suppose we are selling, say, shoes, or we're selling only T-shirts. So what we know our data. So what we do is we train the type of data that we're going to send in the file, and then we create a dictionary out of only those set of data. So we know that we don't have to store the entire dictionary, English dictionary, in a table, but only related to what our data looks like. So that way, if you look at it, even a small JSON is compressed nearly 40% because it knows that our data is going to be of this type. So that way, you're training the model only to compress what we need. Same thing, we audit this is the 4-phase compression. We audit whatever page looks like. There are images, then we compress it, and then we validate if it looks correct. Now, what I explained previously was about texts and paragraphs and sentences, but now we'll move towards compressing pixels, that is videos and images. So AVIF is pretty much older version of it. In 2019, Google introduced it. It works on the same premise as AV1 codecs, which is for videos. And WebP was by Google in 2010. So it's basically older version of AVIF. AVIF compresses much faster. And the next one, which we are going to see, is JPEG XL, which is extremely powerful, and it compresses much faster. If you look at the images, so they did some studies on what actually a human eye perceives more is the brightness. So if you look at an image, if it is brighter, human eye catches faster than if there are small issues in the image or in the texture of it. So what we do first is we actually, if you look at an image, what the algorithm does is it finds what's brightness from a RGB value. So it separates both of them because it knows that we have to assign a more emphasis to brightness rather than to some texture which is red, green, or blue, because our eyes cannot differentiate them. For example, images having a hairs or there is a beard or something, we can go and we can blur it a little bit because that's not visible, but the brightness is more visible. So we separate the brightness with the RGB. Then we basically do a chroma subsampling. It's essentially assigning weights, more number of weights to images which are having textures. Then we do split this image into multiple blocks of 4x4 tiles or 8x8 tile. And then what we do is we do quantization, basically assigning bits to it. And then in the end, we basically do the same thing that we do with the entropy, basically assign bits and store it in the file. Just two more slides to go. So here, what's the difference, right? So WebP does digital cosine transformation like JPEG, but it does only for 8x8 images. There's a loss here because we are resetting the entropy a little higher so that multiple pixels or textures, they are assigned a common value. So we are losing a lot of data there, but it's not that much visible. And it's 8-bit per channel, and it doesn't support high definition rendering. So next thing that we have here is AVIF, which is the latest by Google. So here, if you see, it does much better compression. It has a color depth of 8, 10, and 12. What it essentially means is that we are assigning more coefficients to images rather than to a brightness of it. So the coefficients are assigned a little higher for brightness rather than to the image. And so which companies have adopted this kind of technology? So if you look at Shopify, which is a popular third-party website for people to start their business on, it uses WebP, which was designed by Google in 2010. It still uses them. It's still faster. Netflix is using AVIF 2019 based technology by Google. It takes 56% of bandwidth savings. We have Facebook, it uses its own algorithm, Z standard. Google uses its own, and then Pinterest is using their WebP plus other technique to load these images. This is my last slide. So what we do currently in our organization is we look at the websites that are currently built. We look where we do A/B testing. We do different. We use different algorithms to see which technology is useful for us. And then there is a sprint which actually is done across different deliverables to see which page runs faster. Yeah, that's all from me. Thank you.
We'll turn to the audience for any questions.
How does cloud plays in the whole picture here? Like we have these edge locations and all, right? Does it add any value with these improvements or?
Yes, of course. So what happens is most of the time we have these algorithms running on Bedrock, Amazon Bedrock. And we have these models that I explained to you about Z standard, right? We know what our data is. Our product catalog is mostly based on different type of products that we get. Basically, it's related, it's assigned whether it's a hazardous product or not, or whether it can be shipped or not to certain countries. So based on that, we build a model on our Amazon Bedrock. And we have cloud as one of the third-party providers which we connect to. And that's how we give it to our inbuilt engine to build a file and test our probability of how the file compression is. So all of these are running on cloud as of now.
Okay, got it. Yeah.
Yeah, thank you, Shailesh. Actually, I mean, I always have the doubt running in behind my mind, like we changing how the data transforming over the years, and we are seeing nowadays every website is, I mean, loading with all the videos. I mean, I was always have the doubt how these guys are maintaining this much of data, this much of highly resolution images in a simple website. How are they doing? But this presentation helped me understand how now from today, like I mean, the way I think when I watch a website will change from this presentation. Yeah, thank you for that, Shailesh.
Yeah, I just wanted to add, when you deploy an application, there is a file which is storing all those HTML tags in it. So when you import an application or when you deploy an application, the lookup file goes with your web page as well. So whenever certain clients hit your website, it does a compression behind the scene. So Google does it itself. So Google as a browser has that entire lookup table stored within itself.
Yep.
That was an insightful session, Shailesh. I have this question. Whenever you do A/B testing, right? So do
Yeah.
you have a set of users or a prefined set of users, or how do you select it?
We have our internal users as well, and we also have our users in different geographical areas where they access our page. So especially Europe, we use extensively, and we also have our team in India as well. So it depends how far the users are, and based on that also we have all these algorithms we run on the same web page, and then we ask users to give us the final metrics of how much fast the web page has rendered. And we also have internal metrics inside, which tells us where the user is accessing, where it is clicking, and it shows us internally as well. So it's automated as well to some extent.
Yeah.
Hey, Shailesh, thank you for presenting this topic. It is really insightful. I have a question. Like, you mentioned about the quantization in one of the slide.
Yes.
Can you a little bit elaborate about how that part is affect this web search part?
Yes. So I'm sharing my screen again. You're able to see, right?
Yes.
So on the screen, right, you're seeing the tree structure here.
Yep.
So if you see here, this tree structure is storing T. For the T, the value, the value for the bit is, for T is 10 bits, right? And then for A is 11 bits. So every letter has a bit assigned to it. And if you look at the quantization here, it's actually 2 bits of value. It's actually assigning 2 bits to each and every string, each and every letter, which is not going to repeat extensively. So this is quantization. We are basically assigning bits to it. But if you go to something like LZ compress, if you see here, if it says greater than or equal to 1 bit, symbol is a wasted, because what you're doing is you're assigning 1 bit to a value where you can also assign 0.05. Right. So what we're doing, quantization, is basically making the value a little lower so that we can store more values in that particular range. So if you look at some of the models that run on your phone, they are basically quantized to 4 bits rather than 8 bits. So this is where we are making sure that we store fractions as well instead of just entire numbers. And that's why it's a little faster, and it stores a smaller. It actually groups together a larger number of pixels or image attributes into a smaller range, if that makes sense. So instead of a 0 or 1 bit, we store 0.5 bits.
And you are kind of storing the whole information in a smaller or fewer bits, but it does not affect the accuracy or anything.
We do lose to some extent. Yes, we do lose. But then we have to make sure which ones we want to lose. So, that's the reason why we built a tree first, right? That's the reason why we have to go to LZ7 mapping first, because that's how so we don't have to compress. We only want to compress these ones. We don't have to, because they already know where the distance is. So that's why we know where so if this is coming for the first time, we store as it is. Next time we don't store this value. We just store the distance and the length.
Okay. Yep. Thank you. Yeah.
That's the same concept in the database as well, in the compression.
Yes, that's correct. But here we have to do a step just to understand what we have in our file before we
right
find length and the distance.
That's great. So if there are no questions, I like to wrap it up by thanking Alan and Shailesh. Alan, thank you so much for joining us today. Your 4 decades of industry leadership and continued dedication, whatever we have seen, and your dedication and volunteering as like past chair and STEM outreach, we got really inspired. We are especially grateful for you sharing the details on the Mission Tomorrow event. It's really a powerful example of real world STEM impact, and we really appreciate your insights on empowering the next generation of engineers.
Thank
We
you.
are truly privileged. And Shailesh, thank you so much for the fantastic presentation on web performance. For me, at least, it's an eye opener because I mostly deal with backend. So definitely, audience took a bit or two more on the web performance end, and especially your breakdown of the next gen compression. That was the key, I believe, which the world needs to move towards to. And then your context modeling, and then the Z Sanders FSE engine was exceptionally clear. Maybe, I mean, we got a lot of it by listening rather than reading it ourselves. So bridging
Thank
the
you so
gap
much.
between the raw data compression and algorithms, you really nailed it. Thank you so much for coming and presenting. Yeah.
I appreciate it. Thank you very much.
So we will again meet 2 weeks later with another great session. So please follow, and then we can meet you again. Thank you so much.
Yeah.
Thank you.
Thank you.
Yeah,
Thank you.
you are.
Thank you.
Thank you.
Thanks. Bye.
Bye.
Bye.